Example 7.4. Describe physically the behavior of the inductor's current. Does it store or decay current? Calculate and plot the current of I12 for all times. A. I want to interpret the behavior of the inductive current. Or t equal to 0 minus and t equal to t infinity. Well, actually, it can't be because we have two switches. So it's got to be t equal to 0 minus between 0 and 51 milliseconds. And then finally, for t greater than 51 milliseconds, which I really mean t infinity. So here we go. So if I look at my circuit, here's what I'm looking at. At t equal to 0 minus, you could see here is that the switch to the 52 volt source is open and the switch to the 6 ohm resistor is closed. So then my circuit looks something like this. So I'm going to have two resistors in series. Then I'm going to have this 6 ohm right here. And then there's going to be my short of my inductor. So here's my 52 volt source. And then right here, this is my inductive current right there. Now, because this is happening, I'm going to have to be careful with my notation. I'm going to call that IL of 0. So in this case, this circuit contains the 52 volt source. Now look what happens. At t equal to 0, the 52 volt is shorted out. So when I look at this time interval, the 6 and the 52 volt source are now gone. So I now have a circuit that looks like this here. So I have a resistor here. And then I have another resistor right here. And then I have my inductive short here. So what you're seeing here is that now, at this point, I'm going to have this new inductor that has this behavior right here as a function of time. So what you're seeing here is that I have no source and no source, and therefore the inductive current decays. What that really means here is that IL of 0 is going to be larger than IL of 1 at any point, except where at the boundary. So it's going to decrease. And then the second switch is thrown. So at T51, you're going to see here is that this 6 ohm is now going to disappear from the circuit. So at T greater than 51 milliseconds, you're actually seeing a circuit that goes from a low resistance because these two resistors are in parallel, and then I'm going to go to a higher resistance because there's no more 6 ohm. So when I look at the circuit, I'm looking at this here. So I have this resistor, and then I have my short. So now I'm looking at this current right here, and this is going to be this guy. So this circuit has higher resistance that causes the inductive current to decay faster. So if I now look at everything here, what I'm really seeing here is that I'm seeing that IL0 at 0 minus is larger than IL1 between this guy, which will then be larger than IL2 for t greater than 51 milliseconds. So looking at the circuit, this is what we expect. So now we see that we have three regions. So we see here, so we have three time regions or time intervals caused by the two switches. So now we got to go and we got to look at each of them. So this guy I'm going to call circuit number 0. And this is between the region, of course, minus infinity, t less than 0, which is equivalent to us as t equal to 0 minus. So let's go look at that circuit. So when you look at that circuit right there, what am I actually seeing here? Well, picture-wise, I'm seeing something like this. Let me find my mouse. So if I plug in my circuit right here, here's the actual circuit. So now what I'm going to do here is that I see here is that I have the 52 volt source in the circuit. So if I look at this guy, I'm going to have this guy right here, which is 52 volts. There's a 6 ohm here. And then I have a 12 ohm right here. And then I have my 6 ohm right here. And then I have this resistor. And of course, I have my inductor. So here's my 6 ohm. Here's a 2 ohm. And our goal here is that we want this current IL1 between 0 t and 51 milliseconds. That's what we want to do here. Oh, no. That's not what we want. We want this guy right here at 0 minus. So at 0 minus, that means the inductor becomes a short. So we then see that at t equal to 0 minus, the inductor is a short, which implies here is that the inductor at 0 minus is the same as the current of that 2 ohm resistor at 0 minus. And the other thing that we want to look at here is that note that we have this current I12 at 0 minus. So what we want to do here is that we want to determine two things here. So we want to determine IL of 0 at 0 minus, which is the same as I2 of 0 minus. and I12 of 0 minus. So let's go do that. So when I look at that circuit here, I want to do two things. To get the initial inductive current, I'm going to use voltage divider rule to get the voltage where the 6 and 2 are in parallel. And then I'm going to use Ohm's law to then get that current right there. So I'm going to do this process that goes like this. So I'm going to use VDR to get V6 parallel to 2, but note that this is exactly the same as the 2 volt, this is a 2 ohm resistor, and Ohm's law to get I L naught of 0 minus, which is the same as I2 of 0 minus. So here we go. So the first thing that we're going to do here is this tells me that VDR then tells me that the voltage between the 6 and the 2 in parallel is then going to be 2 parallel to 6. But remember, this is series now. So this is going to be 6 plus 12. And this is going to get divided into 2 parallel to 6 times 52 volts. So when I compute this, I get plus 4 volts. And that's the voltage of the 2 ohm resistor. So then I know that the current of the 2 ohm resistor then has to be the resistance divided into this voltage. And when I compute that number, that's going to be 4 divided by 2. So I'm going to get 2 amps. And that's going to be my inductor value right there. So there's my initial condition for the inductor there. So then I want to get that current of the 12 ohm resistor. So I'm going to use the exact same process. So I'm going to use the same process as before. So the way I'm going to use that same process, note that this is again a series circuit. So I'm going to focus on VDR, and I want the voltage across the 12 ohm resistor. So if I want that, then using voltage divider rule, I'm then going to have what? 2 parallel to 6 plus 6 plus 12. But now it's into 12. And when I compute that, I get a value of 32 volts, which is the voltage of the 12 ohm at 0. So now I want that current. So to get that current, I know that I12 of 0 minus should be 112 times the voltage of the 12. And when I compute that, that gives me 8/3. 8/3 of an amp for I12 of 0. So now I have my initial conditions right here. So now that I have my initial conditions, I'm then going to go in and I'm going to throw the switch. So now my switch is going to be thrown and I have a new circuit. I'm going to call this circuit number 1. And this is between the time interval 0 and 150 milliseconds here. So when the switch is thrown, it shorts out the 52 volt source. So when I look at this, I think I still have that circuit. Let's paste that in. You can see here is that this is going to short it out right here. So then that kills that, and that kills that. So then my circuit really looks like this now. I have this. So I have this resistor. I have my 6. Then I have my 2. And then I have my inductor. So here's my 12, my 2, and here's my 6 ohm. And we are interested in this guy. We're interested in two currents. We want IL of 1 between 0 t and 51 milliseconds. And then we want this guy, I12, as a function of t for that interval. So when we look at this thing, it's clear that 1 immediately sees no source in the circuit. So that immediately implies that we have a decaying current. So here we go. So now I need to determine the Norton parameters at t equal to 0 plus. So let's go do that. So what I see here is that, so the first thing I'm going to do here is that I need to determine I short circuit 1, right? I need to determine that. Nope. I want the initial condition first, right? Do I want to do that first? Nope, I'm gonna not determine the Norton parameters yet. The first thing that I got to do here is that I have to determine IL1 at 0 plus. So what we see here is that because inductive currents cannot change instantaneously, then what we see here is that then IL of 0 at 0 minus must be IL1 at 0 plus, but we already computed that, and that is 2 amps. So I now know what this initial condition is right there. So now that I have that, now what I need to determine here is the Norton parameters. So here we go. So the first thing that I'm going to go after is I'm going to determine I short circuit 1. Okay. So here I go. Again, this tells me that there's no source. If there's no source, that tells me that we have no choice because nothing's feeding the inductor. That is 0. So now we know that. So then the next thing that we want to do is that we want to determine the Norton resistance NR1 and 1 over tau 1. So let's go do that. So if I look at the circuit, what am I seeing here? Well, if I remove the load, then I have this resistor. And so this is the 12, the 2, the 6, And you could see here is that this is my Norton resistance right there. So then this tells me here is that the Norton resistance, you could see here is that if I follow the current, I'm going to have 2 plus 12 parallel to 6. So when I compute that, I get 6 ohms for Rn1. So then that tells me here that my time constant, which will be 1 over tau 1, is then going to be Rn1 times divided by L, which this will be 1 Henry. So then I'm going to get 6 hertz, and that's going to be 1 over tau 1. So now I have all of my details about writing the thing here. So now what I'm going to do here is that I'm going to put the inductor solution into proper form. So then I see that IL1, and I'm just going to write T for right now. This guy has to be I short circuit 1 plus IL1 at 0 minus I short circuit 1 times e to the minus t over t1. So when I write this out, we can immediately see that this guy is 0, this guy is 0, and we know that the initial condition was 2, so then this becomes 2 e to the minus 6t amps, and this is IL1 between 0, t, and 51 milliseconds. So now I have my inductor solution right here. So now that I have my inductor solution, I now want to go in and I want to calculate the current I12. So look what I'm going to do. I'm going to grab this guy right here because that's our circuit. I'm going to copy this and I'm going to bring it right down here. So now what I'm going to do now is that I want to calculate I12 between 0, t, and 51 milliseconds. So if I bring in my circuit here, this is what it looks like. And look what I'm going to do. I'm going to erase all of this just to make it a little bit more compact. And what you're seeing here, if I look at I12 coming in, it's split between the 6 and the 2. So what I'm going to say here is that the I12 of t acts like a source current. Right? If it acts like a source current, we can apply CDR to get I12 of t here. So if I look at CDR, look what it says here. So CDR says this. So CDR tells us that if I want the current of the 2 ohm resistor, that has to be the opposite resistance, which is 6 times the source here, I12. But note, this is the same current as the inductor there. So now what I'm going to do here is that I'm going to solve for I12 of t. And so when I do that, I'm just going to obviously bring it to the other side. So I'm going to get 8 over 6, which is the same as 4/3. So then I'm going to get I12 of t is going to equal 4/3 times 2e to the minus 6t, which then gives me 8/3 amps, nope, 8/3 e to the minus 6t amps, and this is I12 between 0 and 51 milliseconds. So now I have my current of the inductor and the 12 ohm resistor. So now our second switch is thrown. So now what we have here is we have our third circuit, which I've labeled 2, and this is for t greater than 51 milliseconds. So let's look at this here. Oh, I do not have that, so I need to go get it. I want to put in the circuit, and here it is. So here's my circuit. So now look what happens here. So when I throw this, so the first switch did what? The first switch killed this one and this one off. Now the second switch does what? It kills off the 6 ohm resistor. So what I'm seeing here is that the circuit that I have has the 12, the 2, and the inductor. So in other words, our circuit really looks like this. This is our circuit. So I have my 12 ohm, I have my 2 ohm, and I know that this guy is going to be I12 as a function of time. And then I have my inductor current, which now I'm going to call this IL2 of t. Now remember, all of this time is for times greater than 51 milliseconds. So now I got to go through the process here again. So the first thing that I got to do here is that I got to determine the initial condition for this circuit here. So here we go. So I need to determine IL1 at t equals to 51 milliseconds. That's my initial condition. So if I look at this guy, what am I seeing here? Well, I see here that because this is an inductor current, this tells me that the previous current must match at the boundary. So in other words, IL1 at t equals to 51 milliseconds must equal IL2 at t equals to 51 milliseconds. But we don't know what IL2 is, so then I only use the solution for I use this solution right here, which is 2e to the minus 6t. So then if I plug this in, note that this should be 2e to the minus 6 at 51 milliseconds. And when I compute that value, I get 1.47 amps. And that's IL1 at 51 milliseconds. So I now have my initial condition. So then the next thing that I got to do here, sticking to our process, we want to determine the Norton parameters. At t equals to 51 milliseconds. And I'll put a plus there. So here we go. So if I do that, first thing I'm going to do here is that I want to determine I short circuit 2. And again, this is fairly straightforward because there's no source. So there's nothing supplying the inductor. So that means that I short circuit 2 must be 0. So we now know that. So then the next thing that we want to do is that we want to determine our N2 and 1 over tau 2. So look at our circuit. We got if you look at our circuit here, we got a 2 and a 12 in series. So if I draw this out, I have this guy. So here's our 12, here's our 2, and then this guy right here is Rn2. So if you look at this resistance compared to the other resistance, note that this is in series. And if you look at the other resistance, this is in series and parallel. So this is going to give me, this is, when the switch is thrown, this has a lower resistance. This is going to have a higher resistance because it's in series here. So then this tells me then that Rn2 is then going to be 12 plus 2, which is 14 ohms. And then 1 over tau 2 is then going to be Rn2 over L, and L is just 1, so this is going to be 14 hertz, which will be 1 over tau 2. So I now have all my Norton parameters. So now what I'm going to do here is I'm going to put this into proper form. So when I put this into proper form, I now know that I have IL2 for t greater than 51 milliseconds. That has to be I short circuit 2 plus IL1 at 51 milliseconds minus I short circuit 2 times e to the minus, and look what I do. I got to shift it now. I have to shift this in order to get this right here. So now let's put in my values here. So I know that this guy is 0, and I know that this guy is 0. So then if I write out the details, here I go. So what's my initial value? My initial value is 1.47 amps. So then I'm going to get 1.47 amps. And then look at that. I'm going to get e to the minus 14 t minus 0.051 amps. And this guy is IL2 for t greater than 51 milliseconds. Now let's go get I12. So I need to determine I12 for t greater than 51 milliseconds. So when I look at this thing, look at the circuit here. Note that the I12 and the inductor are in series. So the 12 and the inductor are in series. So this is pretty straightforward then. This just tells me that I12 for t greater than 51 milliseconds has to be the same as this guy for t greater than 51 milliseconds. So that was straightforward. Now let's get to the details here. So the first thing I want to do here is that I want to now summarize plot and interpret. I12 as a function of t. So if I put everything together, here's what we find. I have that the current starts at 8/3 amp at t equal to 0, and then a switch is thrown, and it becomes 8/3 minus 6t amps. And then we see here that this guy goes to 1.47 e to the minus 14 t minus 0.051. So this is for t at 0 minus, this is for 0 t and 51 milliseconds, and this is for t greater than 51 milliseconds. So this tells me that this is the current I12. So here we have summarized our values right here. So now that we have that, we have to ask the important questions. Are there discontinuities at the two switches for I12 of t? So in general, the answer is yes. Resistors have the ability to change instantaneously. So here we go. So the first one I'm going to go after is that I want to look at, is there a discontinuity between I0 minus versus I12 at 0 plus? So I can look at my solutions here, and this is what it tells me. It tells me that I12 of 0 minus is equal to 8/3 amps. And then I'm going to compare this to I12 at 0 plus. So this is really 8/3 e to the 0, which of course gives me 8/3 back. So immediately we could see here that there is no discontinuities. There's no discontinuity. So that's a smooth transition. So now let's look at the next switch here. The next switch occurs at 51 milliseconds. So look at my notation now. I'm going to use the same type of notation. So it's going to be I12 at 51, look at my minus sign, milliseconds. That's right before the switch is thrown, versus I12 at 51 plus milliseconds. So I'm separating these guys. Let's go compute this then. So if I go and I compute this, remember I got to stick to these equations that's going to tell me this. So I'm going to have what? I'm going to have I12 at 51 minus. This is going to give me, so I got to go to the situation between at the switch. So before the switch is thrown, this is 8/3 e to the minus 6, but now I got to put in my 51 milliseconds. So when I compute that, I get 1.97 amps. So now I have to compare it to what happens after the switch. So this is I12 at 51 plus milliseconds. So now I have to look at the second solution. So this guy is 1.47. Then I have e to the minus 14. And at that, look what I get. I get 0.051 minus 0.051, which gives me 0. So this guy ends up as 1.47 amps. Look at this. You could see if I compare here to there, we clearly see different values. So here, there is a discontinuity. So when we graph that, we have to include it. Now, let's go plot this thing here. So now what we want to do here is that we want to plot this correctly. So here we go. So remember, I'm plotting this guy right here. So here's what we're going to do. So the first thing you should do, we have the following thing. I have my current going like this. And here's what I'm going to see. So this is I12 of t. So the first thing I see here is that at 0 minus, it's at 8/3. And note that it's going to be smooth here. So I'm going to put this guy to be 51 milliseconds. So I have a current coming in here. And this is IL0 minus, which is 8/3. So I see here is that I have a constant current flow that's happening. Oh, I made a mistake here. Because note, that is 12. That's not the inductor that we're plotting. And then there's a smooth transition. So if I look at the smooth transition here, I'm going to come here. And what you're seeing here is that this here is then, it's going to then go down to 1.97 amps. So that means that if I look at this guy right here, this is 1.97 amps. And this is really I12 at 51 minus milliseconds. Okay, so you're seeing here that there is a decay here that's occurring right in here. And then all of a sudden, the next switch gets thrown. And as the next gets thrown here, this guy drops to a discontinuity. And this discontinuity right here, this has a value of 1.47 amps. So because I have that value here, now note that when we looked at this, if we looked at the time constant, note that this is a higher time constant. So now it's going to decrease even faster now. So then there's going to be a decay that's even faster, and it's going to follow this path right here. So when I look at this, this is the region of I12 between 0 t 51 milliseconds. There's a discontinuity, and the discontinuity then brings me to IT greater than 51 milliseconds. And that's the graph.